Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about the correlation coefficient. Our goal is to describe some important properties of the correlation coefficient. The prerequisites for this material are correlation and linear estimation. Let's first review everything we have already learned about the correlation coefficient. We have seen that we can define the correlation coefficient as the covariance, so the correlation coefficient between two random variables, A and B. We can define it as the covariance between A and B, which equals the expected value of A minus its mean times B minus its mean. So we multiply the centered random variables and then we take an expected value. In order to obtain the correlation coefficient from the covariance, we have to divide by the standard deviations of A and B. We also covered the connection between the correlation coefficient and linear estimation. In particular, if we consider the standardized versions of A and B, where we have subtracted the mean and divided by the standard deviation, then the best linear estimate of SB, standardized version of B, given the standardized version of A, is just scaling the standardized version of A by exactly the correlation coefficient. So it tells us what scaling factor we have to apply to the center normalized version of A in order to estimate the centered normalized version of B. It is also connected to actual linear estimation, where we don't center or standardize and we just want the best estimate of B given A. That best estimate of B given A we derived in a previous video to be equal to the correlation coefficient times the standard deviation of B times the standardized version of A plus the mean of B. You might realize that this is not linear, this is affine, but nevertheless we usually call this the linear minimum mean squared error. That's what this MMSE means, estimate of B given A. Okay, so this is what we have covered up to now. Now, in order to derive the properties that we want to cover about the correlation coefficient, we are first going to look at the mean squared error of the best linear estimator of B given A. Okay, so we're going to call the best linear estimator like this, but we know that it actually has this expression, but this is just easier to write. So this is the best linear estimator, and we're going to see the error it has. So how well does it approximate B in mean squared error? We just plug in the expression, and now we're going to group B and its mean, and we're going to multiply and divide by the standard deviation in order to get the standardized version of B, because that is going to simplify the expression a lot. Okay, so now we take this sigma B out. This is what is happening in this step. And we realize that here we have the standardized version of B. Okay, so now we have the correlation coefficient times the standardized version of A minus the standardized version of B, which, if you realize, is the mean squared error of the standardized linear estimate, right? Because this standardized linear estimate tries to approximate the standardized version of B using exactly this linear estimate. Okay, so now we're going to expand this square and apply linearity of expectation. This is the square of the first term, correlation coefficient squared times the mean squared of the standardized version of A, plus the mean square of the standardized version of B. This is the square of the second term, and then applying linearity of expectation, and then we have the cross term. Okay, so remember that when we standardize, the standardized random variable is zero mean and unit variance. So the mean square is equal to the variance, which is equal to 1. Same thing for the standardized version of B. This is going to be equal to 1. And here, the expected value of this product is the expected value of the product between the standardized version of A and the standardized version of B. That is exactly equal to the correlation coefficient. In fact, this is another way of defining the correlation coefficient. This is how we define the correlation coefficient originally in order to connect it with linear estimation. So we obtain this very nice expression. So just to be clear, so here this is equal to the correlation coefficient. So this is minus 2 times the correlation coefficient squared. This guy is equal to 1. This is equal to the correlation coefficient squared. So when we put everything together, we have that the mean squared error of the best linear estimate of B given A is exactly equal to the variance of B times 1 minus the correlation coefficient squared. So the correlation coefficient immediately tells you how good the best linear estimate is going to be. Now, based on this result, we can analyze the residual. We realize that the mean squared of the residual is equal to this. This is what we have just derived. And now we're going to look at its mean and its variance, because this is going to help us to establish the properties of the correlation coefficient that we want to talk about. Okay, so first, let's look at the mean. In order to derive the mean of the correlation coefficient, we're going to plug in the expression for the best constant term. You're gonna you might have to look back to the video on linear estimation, but it turns out that this best constant term is just equal to the mean of mu minus alpha prime the mean of mu a. Where does this come from? It comes from the fact that the best constant approximation to a random variable is equal to its mean. But again, you can look back at that video if you want to remember this, and it's just this expression. So when we plug it in, this is the expression that I just alluded to. What we see is that the mean of the residual is equal to the mean of alpha prime a minus alpha prime a times its mean plus the mean of b minus b, and we're taking expected value. So when we apply linearity of expectation, everything is going to cancel out. This guy and this guy are going to cancel out, and this guy and this guy are going to cancel out. So the residual is zero mean, which by the way makes a lot of sense, because if the residual was not zero mean, then you would just take its mean and add it back to the linear estimate to improve it. Okay, so it makes a lot of sense that the residual is actually zero mean. Now, what is the variance of the residual? The variance of the residual is just equal to the mean square of the residual, because it's zero mean. And we have just seen that the mean square of the residual is equal to the variance of b times 1 minus the correlation coefficient squared. And now we're going to use these results to establish three very important properties of the correlation coefficient. The first important property are some bounds on the correlation coefficient. In order to establish these bounds, we are going to use the fact that if you have the expected value of a non-negative quantity, then that expected value is always going to be non-negative, because when you're computing the expected value, you take that quantity, you weight it by probabilities or probability densities, and you take a sum or you take an integral. So if you're taking a sum or an integral of non-negative quantities, the result is going to be non-negative. That's why the expected value of a non-negative quantity is always non-negative. How are we going to use this? Well, we have established that the mean squared of the correlation coefficient is equal to this quantity. But this mean squared is actually the expected value of a non-negative quantity, because this guy is squared. So this means that this quantity is always non-negative. The implication is that unless the variance of b is 0, then the square of the correlation coefficient is always smaller or equal to 1, which means that the correlation coefficient is between minus 1 and 1. You might say, but wait a minute, what if the variance is actually 0? Remember that the variance cannot be negative, because it's the square of a certain quantity. If the variance is 0, then it turns out that b is just equal to its mean. It's just equal to a constant. This is not a very interesting, it's not an interesting random variable. The covariance with any other random variable is just going to be 0. So we can ignore that case. Okay, so it turns out that the first important consequence, or the first important property of the correlation coefficient, is that it's always bounded between minus 1 and 1. So you can, in a way, see it as if we had taken the covariance and normalized it, so that this quantity that captures the correlation between two quantities is invariant to the standard deviation and the mean of the quantities, which makes a lot of sense, right? Because we also defined it as the correlation between the standardized version of the quantities. This confirms that the correlation coefficient is a normalized way of quantifying correlation. It's always between minus 1 and 1. Let's move on to the second important consequence. So let's think about what happens if the correlation coefficient is exactly equal to minus 1 or exactly equal to 1. We know that it's between minus 1 and 1, but it could be equal to minus 1 or equal to 1. Well, in that case, what's going to happen is that the variance of the residual which we know is equal to this quantity, the variance of B times 1 minus the correlation coefficient, that variance is exactly equal to 0. So as I mentioned actually briefly a moment ago when I was talking about what happens if the variance of B is 0, it turns out that by Chebyshev's inequality, we covered this when we looked at Chebyshev's inequality, if the variance of a certain random variable x is 0, then that random variable is equal to its mean with probability 1. So now you can think of the residual as the random variable x. The mean of x in this case is 0. We have seen that the mean of the residual is 0. So if the variance is 0, which happens when the correlation coefficient is equal to -1 or 1, then the residual is equal to 0 with probability 1, which implies that B is just an affine function of A with probability 1. This is a very strong statement. If the correlation coefficient is 1 or -1, B is completely linearly related to A. And the way we can connect, because remember that the correlation coefficient has to do with expected values, but this says something about the random variable with probability 1. We achieve this connection through Chebyshev's inequality. So this is the second important consequence of our analysis of the residual. In order to illustrate it, let's see what happens if you look at samples of two random variables A and B as we crank up the correlation coefficient towards 1. So here the correlation coefficient is 0.95. Here are like, I think, 1,000 samples. These are the samples if we crank it up to 0.99, 0.999, and 0.99999. So we see that the samples almost lie on a line as predicted by our results. In the limit where we approach 1, then they have to lie exactly on that line. This is what we mean when we say that B is linearly related to A with probability 1. Okay, so in order to establish the third important... Wow, I don't know what happened there. I don't know if you saw that there was some ghost number appearing here. Anyways, let's move on. In order to establish the third important property of the correlation coefficient, we're going to consider a decomposition of B into the linear estimate and the residual. And we're going to see that the fraction of variance in each of these components is determined exclusively by the correlation coefficient. What I mean is the fraction of variance of B that goes into this component. But for this to make sense, we first have to study what the variance of a sum is equal to. Okay, so, and you'll see why in a moment. So what is the variance of A and B? A plus B, sorry, of the sum of A plus B. By definition, it's A plus B minus the mean. Now we're going to expand out this mean by linearity of expectation, and we get A minus its mean plus B minus its mean. Now we're going to expand the square, so we get and apply linearity of expectation, get the expected value of the squared centered version of A, the mean square of the centered version of B, plus 2 times the expected value of this product. Now, by definition, what are these guys equal to? Can take a moment to think about it. Well, this is just, the first one is just the variance of A. The second one is just the variance of B, and this guy is just the correlation between A and B. So we get a very interesting expression where the variance of a sum is equal to the sum of the variances plus twice the covariance. This kind of gives you a little bit of an intuition about what the covariance captures. If you think about how two random variables fluctuate together, if the covariance is positive, then they fluctuate together. They fluctuate together, so that there's constructive interference between them. And when you sum them up together, the variance of the sum is larger than the sum of the variances. If they're inversely correlated, they kind of cancel each other out, so that when you sum them up, the variance of their sum is smaller than the sum of the variances. And then when they are uncorrelated, what happens? Well, the variance of the sum is exactly equal to the sum of the variances because the fluctuations do not interfere either constructively or destructively. Okay, so why am I telling you all of this story? Because we're going to see essentially that the linear estimate and the residual are uncorrelated. So then we can just divide the variance of B into the sum of these two variances. So in order to understand why they should be uncorrelated, first let's think about whether the residual and A can be correlated. Think about it for a moment. If the residual and A were correlated, then essentially that would mean that there's some linear dependence between the residual and A, which you could exploit to estimate A from the residual. But then you could take that and add it to the linear estimate to improve the linear estimate, which cannot happen because the linear estimate is the optimal linear estimate in terms of mean squared error. Okay, so that's an argument why it should not be possible. That's an argument why the residual and A should not be correlated. So let's prove that that is indeed the case. Let's consider the covariance between A and the residual. Remember that the residual is zero mean, so we have A minus its mean times the residual minus its mean. The residual has zero mean, so that's easy. So now we're going to take out, we want to divide and multiply this term by the standard deviation in order to get the standardized version of A. Okay, we obtain it here. Now we see that here we have B minus its mean. Once we plug in the expression for the best linear estimate, we also want to get the standardized version of B because it's going to make our life easy. So we multiply and divide by sigma B. We see that we have this sigma B and this sigma B, so that it can just come out. And we end up with an expression where inside the expectation we have this product of the standardized version of A times S of B minus the correlation coefficient times S of A. So now applying linearity of expectation, we can just group these guys. What is the expected value of this product? It's the correlation coefficient. In fact, it's our original definition of the correlation coefficient. So we have the correlation coefficient minus this correlation coefficient can come out, this term, and the mean squared of the standardized version of A is just equal to 1 because its mean is 0, so the mean square is equal to the variance, and the variance is 1 because it's standardized. So correlation coefficient minus correlation coefficient is equal to 0. Indeed, like we expected, the residual is uncorrelated with A. Sorry about that. I try to avoid this, but it happens sometimes. It's obvious, right? It says are uncorrelated underneath. Anyways, the covariance between the best linear estimate and the residual is equal to the expected value of the linear estimate minus its mean. Okay, so this is just by linearity of expectation. When you apply linearity of expectation to this, this is just a constant, this is just a constant. So we have that this guy and this guy are going to cancel out, and we can bring out the coefficient. It's therefore proportional to the covariance between A and the residual. Okay, this is just equal to alpha prime times the covariance between A and the residual. We have just proved that the covariance between A and the residual is 0. This makes a lot of sense, right? If A and the residual are uncorrelated, any affine function of A and the residual are also going to be uncorrelated, and this proves it. Okay, so they're uncorrelated. This means that now we can apply this result that the variance of the sum is equal to the sum of the variances. We can separate the variance of B into the variance of the linear estimate and the variance of the residual. We have already derived the variance of the residual is just equal to the variance of B times 1 minus rho squared. So now we can look at the variance of the linear estimate, which in a way is the variance that is explained linearly. Okay, this is where explained variance comes from, like you might have heard this expression. This is just going to be the variance of B minus the variance of the residual. But the variance of the residual is 1 minus the correlation coefficient squared times the variance of B. So this is just equal to the correlation coefficient squared times the variance of B. So this is the fraction of variance that goes to the linear estimate. We can therefore interpret the correlation coefficient as the fraction of variance that is explained linearly. And this is the third very important property of the correlation coefficient, and maybe it's the most useful. So directly, if you know that the correlation coefficient between two quantities is high, that means that when you look at the amount of variance that you have in your data, a lot of it is going to be explained linearly. Okay, so let's look at an example. Here we have a correlation coefficient of 0.95. This is the original data. This is the linear estimate of B given A, and this is the residual. By the way, realize that the residual does indeed look uncorrelated with A. There seems to be no linear dependence. Now we're going to look at the variance of B, the variance of the linear estimate, and the variance of the residual. And as expected, the fraction of variance that is explained is equal to the square of the correlation coefficient. When the correlation coefficient is smaller, this is exactly the same. So again, we want to estimate B from A. This is a scatter plot between B and A, the linear estimate as a function of A, the residual as a function of A. And now less variance is explained. This is the square of 0.25, and the residual has more variance. If the two random variables are uncorrelated, in this case, we just give up, right? When we are doing the linear estimate, we say linear estimate is just equal to 0. The residual is exactly equal to the original data, so that now the variance of the residual is 1, the variance of the linear estimate is 0. Now we're going to look at a real example where we're estimating rebounds from height. This is the scatter plot of the data. This is the density, because it's just easier to see, right? If you just look at the scatter plot, it's unclear that there's more density of points there. And this is the standardized density. We could have just shown the density itself, but I don't know. Now, this is the linear estimate. This is the standardized data, density of the data, and this is the residual, which again is uncorrelated, okay? It's uncorrelated with the original data. If we look at the variance, the variance of the original data is equal to 6.19. The variance of the affine estimate is equal to 1.10. This affine estimate is just the best linear minimum mean squared error estimate. And the residual is equal to 5.09. Here, if you remember, the correlation coefficient is equal to 0.42. Okay, so the fraction of this 6.19 that is accounted for by the linear estimate is equal to 0.42 squared. Same for assists and height. In this case, the correlation coefficient is minus 0.46. Again, we're asking ourselves how much variance is accounted for by this linear estimate. Again, this is the residual, which is uncorrelated with the original data. See that it has been shifted so that it becomes uncorrelated. There's no linear dependence on average. We see now again that the variance that is explained by the linear estimate is equal to the correlation coefficient squared times the original variance. Okay, I just wanted you to visualize exactly what we're talking about when we're saying about explaining variance and so on. In this case, with points and height, if you remember, the correlation was very, very low. It's minus 0.06, I believe. So in this case, when we look at the linear estimate, we see that there's just a very slight correlation. And the variance explained by the linear estimate is very, very low. Okay, so this shows you that the correlation coefficient does not only tell you the slope of this linear estimate and so on, it actually tells you how much variance is explained in the original estimate, and the variance is kind of a proxy for how much of the energy in the original data is accounted for in the linear estimate. Okay, so what have we learned? We have learned that the correlation coefficient between two quantities is always bounded between minus 1 and 1. It implies complete linear dependence if it equals plus or minus 1. Complete linear dependence, right? Like that was not English. And it equals the fraction of the explained variance captured by the linear estimate. Or rather, its square equals the fraction of variance explained by the linear estimate. Thank you very much.